Look up at a clear night sky, and you are seeing almost nothing. Every star you can name, every galaxy captured by every telescope ever built, adds up to a small fraction of the universe's total mass. The overwhelming majority is invisible. It emits no light, absorbs none, reflects none. We cannot photograph it, we cannot bottle it in a laboratory. And yet it is there, outweighing all the glowing matter in the cosmos by roughly 5 to 1. Scientists call it dark matter, though the name is really a confession of ignorance. We do not know what it is, we know only what it does. It pulls. Consider the problem plainly. A spiral galaxy is a vast pinwheel of hundreds of billions of stars spinning through space. Gravity holds it together, and gravity depends on mass. Count the visible stars, weigh the glowing gas, and you can calculate exactly how much gravity the galaxy should possess. For most of the 20th century, astronomers assumed that the light they measured told them the whole story. Where there was brightness, there was mass. Where there was darkness, there was empty space. That assumption turned out to be catastrophically wrong. The universe, it emerged, keeps most of its substance hidden. The stars are merely the foam on a far deeper ocean. Dark matter forms invisible scaffolding, threading through galaxies and binding clusters, shaping the very architecture of everything we see. It is an absence made visible only through its effects, a ghost we detect by the fingerprints it leaves on the motion of ordinary matter. And here's the strange truth about how it was found. Dark matter was never discovered by seeing it. It was discovered by watching things that should have obeyed simple laws and finding that they refused. It was discovered in numbers scribbled at a telescope, in velocities that came out impossibly high, and a graph that stubbornly declined to bend the way every textbook promised. The revolution began not with a grand experiment, but with a patient astronomer counting the speeds of stars, one measurement at a time. Her name was Vera Rubin, and almost no one expected her to change the universe. Vera Rubin was born in Philadelphia in 1928, and she fell in love with the sky through the window of her childhood bedroom. She built her own cardboard telescope. She watched meteors and recorded their paths in a notebook. By the time she was a teenager, she knew she wanted to be an astronomer. In an era when women were told, gently and often, that they could not be one. She applied to Princeton's graduate astronomy program and was refused. The department did not admit women. It would not until 1975. So she went elsewhere. She earned her bachelor's degree at Vassar in 1948, her master's at Cornell, and her doctorate at Georgetown in 1954, studying under George Gamow. Her thesis suggested that galaxies clumped together rather than scattering randomly across the sky, a radical idea that the establishment largely ignored. She was accustomed to being ignored. At conferences, she was sometimes the only woman in the room. At one observatory, there was no women's restroom at all. She famously improvised a sign and taped it to a door. Rubin chose her battles with the scientist's patience. Rather than fight for glamorous, contested problems where prestige and rivalry ran hot, she sought quieter corners of astronomy, where careful work could speak for itself. That temperament shaped everything. She was not a theorist chasing sweeping headlines. She was an observer, meticulous, unhurried, willing to spend cold nights at a telescope, gathering measurements one star at a time. She trusted data over fashion. If the numbers said something surprising, she reported the numbers. In 1965, she joined the Department of Terrestrial Magnetism at the Carnegie Institution in Washington. There she found not only steady work, but a collaborator with a remarkable machine, someone whose instrument could pull faint signals from starlight that older telescopes let slip away. Together, they would ask a deceptively simple question about how galaxies spin. Rubin did not set out to overturn physics. She set out to measure something precisely, honestly, completely. The universe repaid that patience with a shock. But to capture the speed of stars too faint for the human eye, she first needed the extraordinary device built by Kent Ford. Kent Ford was an instrument builder, and in astronomy the instrument is destiny. What you can measure defines what you can discover, and Ford had spent years constructing something that measured what others could not. His creation was an image tube spectrograph, and it changed the arithmetic of observation. A spectrograph does something almost magical. It takes the light from a star or a patch of galaxy and spreads it into a spectrum, a rainbow crossed by dark lines. Those lines are the signatures of chemical elements, fixed at precise wavelengths. But when an object moves toward or away from us, the lines shift. Motion toward us squeezes them toward blue. Motion away stretches them toward red. Measure the shift, and you measure the velocity directly, unambiguously, in kilometers per second. The trouble was faintness. The outer regions of a galaxy glow feebly, and traditional photographic plates needed enormous exposures to record such dim light, sometimes many hours or entire nights, gathering photons grain by grain. Ford's image tube solved this. It was an electronic amplifier for light, an early photomultiplier that intensified the faint incoming signal before it struck the recording plate. What once took all night could now be captured in a fraction of the time. Distant, dim starlight suddenly became measurable with precision. Ford's device could resolve velocity differences that older equipment blurred into noise. When Rubin partnered with him at Carnegie, she recognized the opportunity immediately. Here was a tool matched perfectly to her patient, exacting temperament. She could point it at specific regions of a galaxy, gather clean spectra, and read off exactly how fast the stars in that region orbited. Then she could move outward, region by region, and build a complete picture of the galaxy's rotation from center to edge. Together they formed an ideal team. Ford maintained and refined the machine. Rubin designed the observations and interpreted the data. They were not hunting for anything revolutionary. They wanted a clean, uncontroversial project, well suited to a new instrument. They chose the nearest large spiral galaxy, a luminous neighbor sprawling across the northern sky, and prepared to measure how its stars swung around its brilliant core. That galaxy was Andromeda. Andromeda is the great spiral next door, some 2.5 million light-years away, close enough that its disk sprawls wide across the sky, larger than the full moon if our eyes were sensitive enough to see it whole. It was the obvious target. Bright, near, well-studied, it seemed a safe place to test the new spectrograph and settle a routine question about how galaxies rotate. In the late 1960s, Rubin and Ford carried their equipment to the telescope and began the painstaking work. Night after night, they positioned the slit of the spectrograph across regions of Andromeda's disk, gathering light from the stars and glowing gas within. Each exposure captured a spectrum. Each spectrum carried the telltale shift in its spectral lines, and from that shift Rubin could extract a velocity. They worked outward methodically. First the bright central bulge, where stars swarmed densely around the core, then the inner disk. Then farther, into the fainter spiral arms, and farther still, toward the dim outer edges, where the light thins to almost nothing. Every position gave a number, how fast the material there was orbiting the galactic center. The expectation was straightforward, rooted in physics 3 centuries old. In our own solar system, the planets nearest the Sun race around quickly. Mercury orbits far faster than Neptune. This is Keplerian motion. Where most of the mass sits in the center, the outer objects, feeling weaker gravity, move more slowly. A galaxy, everyone assumed, should behave the same way. Its light concentrates toward the middle, so its mass should too. The stars far out in the dim spiral arms ought to be dawdling, orbiting sluggishly, left behind by the bright, crowded, fast-spinning core. Rubin plotted her velocities against distance from the center, expecting to watch the numbers climb and then fall away toward the galaxy's edge, tracing the graceful decline that Newton and Kepler demanded. That falling curve was the whole point, the confirmation of the obvious. But as the measurements from Andromeda's outskirts came in, the numbers refused to fall. They stayed high. Impossibly, stubbornly high. And Rubin, staring at her data, realized something was profoundly wrong. To understand the shock, picture the graph itself. On the horizontal axis, distance from the galaxy's center. On the vertical axis, orbital speed. This is a rotation curve, and its shape encodes where a galaxy's mass truly lies. The predicted curve was clear in everyone's mind. Speed should rise sharply through the crowded central bulge, peak somewhere in the inner disk, and then bend downward, trailing off as you moved into the sparse outer reaches. Less mass out there meant weaker gravity, and weaker gravity meant slower orbits. The curve should fall. Just as Neptune crawls compared to Mercury, the outermost stars should lag far behind. What Rubin and Ford measured did not fall. The curve rose as expected through the inner regions, and then it flattened. It went level and stayed level, a nearly straight horizontal line stretching outward as far as they could gather light. Stars at the distant edge of Andromeda were orbiting just as fast as stars far closer in. In some cases, faster than any reasonable estimate allowed. This was not a small discrepancy. It was a violation of the most basic expectation in gravitational dynamics. If those outer stars moved that quickly, then the gravity holding them in orbit had to be enormously stronger than the visible matter could supply. Speed and gravity are locked together. A fast orbit demands a strong pull, and a strong pull demands mass. Yet the light said the outer galaxy was nearly empty. The two verdicts could not both be true. Rubin checked and rechecked. The image tube spectrograph was precise. The spectral shifts were unambiguous. The velocities were real. There was no error in the machine, no flaw in the method. The stars were genuinely moving too fast. The only escape was to conclude that vast quantities of unseen mass surrounded the visible galaxy, providing the extra gravity, holding the racing outer stars in their orbits. Mass that emitted no light. Mass that could not be seen. The flat rotation curve was a fingerprint, and it pointed to something enormous and invisible. And if this was true of Andromeda, one nearby spiral, then the question became terrifyingly larger. Was every galaxy hiding the same secret? One galaxy could be an accident. Andromeda might harbor some peculiar arrangement of stars, some local trick of geometry. So through the 1970s, Vera Rubin and Kent Ford kept pointing their spectrograph outward, galaxy after galaxy, night after night, at Kitt Peak and Lowell Observatory. NGC 3115, NGC 7541, UGC 2885, a spiral so vast it dwarfed the Milky Way. Each time, the same stubborn signature emerged from the light. By 1978, they had measured the rotation of 10 spiral galaxies. By 1980, that number had grown to 21. The verdict never wavered. Every rotation curve flattened. Stars at the visible edge orbited just as fast as stars nearer the bright central bulge, sometimes at 200, 250, 300 kilometers per second, holding steady where Newton demanded they slow down. Rubin and Ford published their findings in the Astrophysical Journal, and the implication was impossible to soften. If you added up every glowing star, every luminous cloud of gas, every scrap of visible matter these galaxies contained, you did not have nearly enough mass. The gravity generated by what astronomers could see fell short by a factor of 5, sometimes 10. A galaxy spinning that fast, with only its visible matter to bind it, should tear itself apart. The outer stars should fling outward into intergalactic darkness, unspooling the spiral arms like thread from a broken spindle. Yet the galaxies held. They had held for billions of years. Something was gripping them, some vast reservoir of mass that emitted no light, absorbed no light, betrayed itself only through the speed of the stars it commanded. The measurements were clean, repeatable, undeniable. Rubin herself was cautious, reluctant to leap to exotic conclusions, but the numbers spoke plainly. The luminous universe was a minority. The bulk of a galaxy's mass lay hidden, an unseen scaffolding threading through and around everything the telescopes could capture. It was a conclusion so strange that most astronomers hesitated. And yet, if they had searched their own literature, they would have found the warning already written, decades earlier, by a difficult and brilliant man whose measurement of a distant cluster had been ignored for 40 years. In 1933, long before Rubin ever touched a spectrograph, a Bulgarian-born, Swiss-trained astronomer named Fritz Zwicky trained his attention on the Coma cluster, a swarm of roughly 1,000 galaxies, some 320 million light-years away. Working at Caltech, Zwicky measured how fast those galaxies moved relative to one another. What he found astonished him. The galaxies in Coma were racing through the cluster at velocities of 1,000 kilometers per second and more, far too fast to be held together by the gravity of their visible mass. By his calculations, the cluster needed hundreds of times more matter than its glowing galaxies could supply. Without it, Coma should have dispersed long ago, its galaxies scattering into the void. Zwicky reached for a name. He called the missing mass Dunkel Materie, dark matter, unseen substance, whose gravity bound the cluster while emitting no detectable light. He published the idea in a Swiss journal in 1933, then again in English in 1937, and the astronomical community, by and large, shrugged. Zwicky was brilliant but abrasive, famous for calling colleagues spherical bastards, because, he said, they were bastards no matter which way you looked at them. His measurements were rough, his cluster distant and difficult, his personality easy to dismiss. So the warning sat in the literature for 4 decades, a ghost nobody chose to see. Then came Rubin and Ford, measuring not distant clusters but nearby spiral galaxies, star by star, with precision Zwicky could only have dreamed of. Their flat rotation curves and his fast-moving galaxies pointed to the same buried truth from opposite directions. The missing mass was not a quirk of one difficult cluster. It was everywhere, woven into individual galaxies and into the great clusters alike. Rubin's careful, patient work resurrected Zwicky's forgotten claim and gave it a foundation too solid to ignore. Suddenly the ghost had substance. 2 independent measurements, separated by 40 years and utterly different methods, converged on a universe dominated by something invisible. The question was no longer whether dark matter existed. The question became what it was, and where, exactly, it hid. Picture a spiral galaxy not as a flat pinwheel of stars, but as a bright core suspended inside an enormous, invisible sphere. This is the dark matter halo, a vast, roughly spherical cloud of unseen mass that extends far beyond the visible disk, sometimes 10 times wider than the galaxy's glowing arms. The stars we see are merely the luminous sediment, settled at the center of something much larger. It was this halo, its gravity reaching outward, that kept Rubin's edge stars racing at full speed. The halo explained the flat curve perfectly, but naming a thing is not the same as catching it. Since the 1980s, astronomers have hunted dark matter through every tool physics allows. One method is gravitational lensing, predicted by Einstein. Mass bends the path of passing light, and where invisible mass gathers, distant galaxies appear smeared, stretched, or multiplied into arcs and rings. By mapping these distortions, astronomers chart dark matter's distribution directly, tracing its ghostly architecture across the sky. The Bullet cluster, imaged in 2006, showed 2 galaxy clusters that had collided, their visible gas dragged behind while the bulk of their mass, revealed by lensing, sailed on ahead, precisely where dark matter should be. Meanwhile, deep underground, physicists built detectors to catch the particles themselves. In mines and beneath mountains, shielded from cosmic rays, experiments like xenon and lux wait in tanks of liquid xenon for the faint flash of a dark matter particle striking an atomic nucleus. Decades of watching have yielded silence, ruling out candidate after candidate, narrowing the possibilities without a single confirmed detection. We know dark matter outweighs ordinary matter roughly 5 to 1. We know it clumps into halos, seeds, galaxies, and shapes the largest structures in the cosmos. We do not know what it is made of. It passes through us, through the Earth, through everything, felt only as gravity. The halo that Rubin's numbers demanded remains the most abundant, least understood substance in existence. And so the final question turns back to the woman who counted stars, and to what her patient measurements truly revealed about our place in a hidden universe. Vera Rubin never won the Nobel Prize. Many believe she deserved it, and the omission became one of the great oversights in the history of the award. She died in December 2016 at the age of 88, having spent a lifetime measuring the motion of stars and quietly rewriting what we know about the universe. She never claimed to have discovered dark matter. She was too careful for that, too honest about the limits of a measurement. What she said was simpler and, in its way, more profound. The numbers did not lie, and the numbers demanded far more mass than the eye could find. Her legacy is not a particle or a formula, it is a shift in humility. Before Rubin, we could still imagine that the glowing cosmos, the stars and galaxies filling our telescopes, was the cosmos entire. After her, we understood that everything we can see is a thin, luminous froth atop an ocean of the unseen. Ordinary matter, the stuff of planets and people and stars, accounts for less than a fifth of all matter. The rest is dark, silent, and everywhere, holding the galaxies together while offering no light by which to know it. There is a strange grace in this. A woman who was told, early in her career, that certain observatories were closed to her, who built her reputation star by star through patient nights at the eyepiece, ended by revealing that the universe itself keeps most of its substance hidden. We are surrounded by a majority we cannot see, and we learned of its existence only by watching how things move. The stars at the edge of Andromeda spinning too fast were a message written in motion, waiting for someone patient enough to read it. Rubin read it. She trusted the measurement over the assumption, the data over the expectation. And in doing so, she taught us that the deepest truths of the cosmos may never announce themselves in light. They must be inferred, weighed, and traced through their pull on everything around them. In the end, the discovery of dark matter delivered a single enduring lesson. Gravity revealed what light could not.